Okay, hi guys. I'm going to be going over the IB DP Physics Higher Level Paper 2. And question 1 is about this drone that's delivering packages. And the very first question is about stating the value of the resultant force on the aircraft. So remember to read the question very carefully. And at some point it says the aircraft is hovering motionless. Okay, well that means it's in equilibrium, so there's zero net force on it. Easy question, but just read the question carefully. Okay, then we have to outline using Newton's third law how the upward force on the drone is achieved. So of course we know as the blades push the air down, okay, that's happening, right? The blades, as they rotate, they push the air down. Well, then the air is going to be pushing up on the blades, according to Newton's third law. So that's how we explain that. So as the blades push the air down, the air pushes the blades up with an equal but opposite force. That's Newton's third law. Okay, don't just say reaction equals, action equals reaction. Always say something like, when object A exerts a force on object B, then object B exerts an equal but opposite force on object A. Determine V. Okay, so we know that the blades are pushing the air down, and we know that the air went from zero velocity to having a velocity V. And we know that this change in momentum, this rate of change of momentum is equal to the net force. So I know that the momentum of the air has changed in 1 second. So we're just looking at 1 second here. And I know that it was 1.7 kilogram of air that was pushed down in 1 second to achieve velocity V. So I can write this expression for the net force on the air. Now this force on the air, of course, equals the force on the blades, as we have just described. So there's this push going up on the drone, and that has to balance out the weight of the drone. So we can put this force, this expression, equal to the total weight of the drone. So that's what we're going to do. And the total weight is, of course, the total mass of everything times g. And always use 9.8 unless otherwise specified. And we have to give our answer to an appropriate number of significant figures. And you can see all values have 2 significant figures. So we're going to leave our answer expressed in 2 significant figures as well. And you get a point for actually giving the correct number of significant figures here, because they did, specifically ask for it. So yeah. Okay, next one, power transferred to the air by the aircraft. So power is, energy over time. The air's kinetic energy has changed, right? Has increased. And we can work out how much the kinetic energy changed in 1 second. So we know in 1 second it was 1.7 kilogram of air that got pushed downwards. So that's 1/2 mv squared, 1/2 times, and then the velocity it obtained squared. So that's the amount of joules that the air received, and that happened in 1 second. So it's the delta ke over delta t, which is 1 second, and then we work that out and we get the correct answer, which I think was around 56 watts, if I remember correctly. Plug it into your calculator. Yeah. Okay. Next one, now the package and string are released. Okay, so we still have this. So now the drone is not in equilibrium, right? So we still have the lift force from before. But the weight is now lighter because the package and the string are released. So we still have this larger lift force going up and the air pushing on the blades, but we have a smaller weight, so it's going to be accelerated upwards, right? And the amount of acceleration is simply the force from the air that we worked out before minus the new lighter weight, and then we get the answer as around 4.41 newtons, and I should probably round that off just to 4.4 newtons. I think no, wait a second. Yeah, that was just the force, and now the acceleration, of course, we have to divide by mass, which is now only 0.95. Okay, lost the package and the string, and then we leave that. We're going to round this off to 2 significant figures, and that's the right answer. Okay, next question is about this fun amusement park ride, and we have to draw and label the free body diagram. So this person is vertically at rest, okay, so he's not sliding up or down, so his weight has to be balanced out by the friction between him and the wall. So there's weight pointing down, mg, weight, and then there's a friction force pointing up, which is preventing him from sliding down. And then he's of course moving around in a uniform circular motion, so there has to be a net force pointing towards the center, and that is the normal force, right? So the wall is pushing him towards the center of the circle, and that is the necessary centripetal force. Okay. Then we have we have to show that the minimum angular velocity is given by this. So we know that, like I said, he's in vertical equilibrium. So the friction force equals the weight. So friction force equals weight. And then we have to remember how, what's the relationship between friction and normal force. So friction is mu times the normal force, the coefficient of friction times the normal force. That's what friction equals. And from this we can get the normal force as mg over mu. And that normal force is the necessary centripetal force, keeping the person in uniform circular motion. And we know that the acceleration for a uniform circular motion is r omega squared. So m r omega squared equals to this expression mg over mu, and then we can get omega as the square root of g over mu r. There we go. R is the radius. Okay, then now we are given some numbers, some values, the radius and the coefficient of friction, etc. Okay, so 28 revolutions per minute, and that's a speed, okay? Now the angular velocity is 28 times 2 pi radians over 60 seconds, because it's the rate of change of angle, right? Delta theta over delta t, and 28 revolutions means 28 times 2 pi radians, and that happens in 60 seconds. So 2.93 per second, radians per second. That's the angular velocity that he has. And we saw in the previous problem that the minimum angular velocity is given by that expression, so we can plug in all the values and then we'll get something like 2.65, and then we can see the minimum value is smaller than the actual value, so he will not slide down, the person. Okay, so it's a successful amusement ride.